Let's look at the next two examples. In example 5, we have f of x equals x squared plus 9x plus 6 in the numerator, and this is prime, so we're not going to be able to factor this, which means that we don't have to worry about matching factors in the denominator, which is 2 minus x squared. So it appears that we will have some vertical asymptotes for values of x that cause the denominator to be 0. So let's set the denominator equal to 0 to find those troublesome values of x. Using the square root property, we find that x must equal plus or minus the square root of 2, and this will give us the equations of our two vertical asymptotes. X is equal to the opposite of the square root of 2, and x is equal to the principal square root of 2. Now let's go back and compare the degrees of the numerator and the denominator. The numerator has degree 2. The denominator also has degree 2. Since the degrees match, we will have a horizontal asymptote at the line y equals a over b, where a is the leading coefficient of the numerator, in this case an implied 1, and b is the leading coefficient of the denominator, which in this case is a negative 1 because the x squared term is negative. So the equation of our horizontal asymptote is y equals negative 1. In example 6, we have f of x is equal to x squared plus 5x minus 9 in the numerator, which is prime, not factorable. In the denominator, we have x minus 9. So it does appear that we will have a vertical asymptote for x minus 9 equals 0, or in this case, x equals 9. And now let's compare the degrees of the numerator and of the denominator. The degree of the numerator is 2. The degree of the denominator is an implied 1. In this case, because the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. Now let's review two basic functions for which we will do some transformations in the future examples. The reciprocal function f of x equals 1 over x has a very unique looking graph. It's made up of two separate branches, one that sits in the first quadrant and the other that sits diagonal from it in the third quadrant. In the reciprocal function, there are two asymptotes. The x-axis acts as a horizontal asymptote, and the y-axis acts as a vertical asymptote. Recall that asymptotes are imaginary barriers that the graph cannot touch or cross over. It's almost like a repelling magnetic field. Please familiarize yourself with the reciprocal function graph. As I mentioned a moment ago, we will have transformations on this basic graph. Notice that the domain includes all real values of x except for x equals 0 because the x equals 0 line is a vertical asymptote. The range will also include all real values of y except for y equals 0 because the y equals 0 line is the x-axis, which is a horizontal asymptote. Next, let's look at a related reciprocal function, f of x is equal to 1 over x squared. This graph is also unique because it's made up of two separate branches, but these branches occur in quadrants 1 and 2. We also see that the graph is symmetric about the y-axis. In this case, we have the domain including all real values of x except for x equals 0, which is the y-axis, which is a vertical asymptote. And likewise, we do have a break in the graph at y equals 0, which is the x-axis, that is a horizontal asymptote. But the range here would be all positive values of y. So in interval form, it would go from 0 to infinity with 0 not included as a possible value for y. Now let's look at a method for graphing rational functions. This is a step-by-step procedure to make sure that you always have the best graph. The first step is to identify any real zeros of the denominator, so values of the input that would cause the denominator to be 0. This is going to help you identify possible vertical asymptotes. Recall that if zeros of the denominator match a 0 in the numerator, that will not create a horizontal asymptote. It'll create something different, which we'll discuss later. This is going to be called a removable discontinuity or a hole in the graph. Secondly, you're going to identify any possible horizontal asymptotes. Recall that we were going to be comparing the degree of the numerator to the degree of the denominator to do this. In this course, we do not talk about oblique asymptotes. We do discuss that in future courses, but for the purposes of this section, you will not need to know about oblique asymptotes. Step 3, you're going to find zeros of the numerator, and if they do match the zeros of the denominator, we're going to treat those differently. But zeros of the numerator are also going to be x-intercepts, right? So these are values of x that cause the value of y to be 0. So that's going to help us with identifying additional points on the graph. Step number 4, we're going to find the value of the function f when x equals 0. So in essence, we're going to be finding the y-intercepts if possible. And finally, identify other guiding points that will help you get the best shape for the different parts of the graph. All right, let's put this all together in a few examples. Our first example is f of x equals x minus 3 over the quantity x plus 4. Here we see that the numerator and the denominator are already fully factored and that there are no matching factors. So to identify a vertical asymptote, I will set the denominator equal to 0. In this case, we would set x plus 4 equal to 0, which would mean that x equals negative 4 is a vertical asymptote. I'm going to go ahead and add this in green as a dashed line. X equals negative 4 is going to be right over here, and this is going to be an invisible barrier that the graph cannot touch or cross over. Next, let's see if there is a horizontal asymptote present. We're going to compare the degree of the numerator to the degree of the denominator. And in this case, I see that the degree matches. It's 1 in both cases, which means that there will be a horizontal asymptote at the line y equals a over b, where a is the leading coefficient of the numerator, or in this case 1, and b is the leading coefficient of the denominator, also 1. So 1 over 1 will give us 1. I'm going to add this horizontal asymptote as a green dashed line as well. Y equals 1 would be right about here. Probably should make this a little darker so you can see it better, but we see that there is a vertical asymptote and a horizontal asymptote. Next, let's see if we can find the x-intercepts, if there are any. To find the x-intercepts, we're going to set y equal to 0. So in this case, we would set f of x equal to 0. And so we get 0 equals x minus 3 over x plus 4. Well, the only way to get 0 when you divide is if you start out with 0 in the numerator. So that means we're going to set 0 equal to x minus 3. Or in this case, x equals 3. So there is one x-intercept, and it'll be at the point 3, 0. I'm going to go ahead and add that to my graph. There it is. Let's see if there are any y-intercepts. So to find the y-intercepts, I'm going to set x equal to 0. So I'm going to set x equal to 0 in the function, which means I get 0 minus 3 in the numerator and 0 plus 4 in the denominator. So I get negative 3/4. So that means that I do have one y-intercept at the point 0, negative 3 over 4. And let me see if I can find that. That's going to be not quite at -1, so right about there. So I only have 2 guiding points, and I feel like I don't have a good sense of the graph just yet. So I'm going to find some additional points so that I can make sure I have the correct shape. So it looks like it would be helpful to perhaps find out what's happening at x equals, let's say, -2 and x equals -3. So let's see, when x is -2, I have -2 minus 3 in the numerator and -2 plus 4 in the denominator. So that's going to be a -5/2. So let me go ahead and add that to my graph. -2 for x and -5/2 is -2.5. So -1, -2.5, right about there. Okay, so now I'm getting a sense that I'm going to have a branch here in this corner. And just to confirm that, let me go ahead and find f of -3. So that'll give me -3 minus 3 in the numerator and -3 plus 4 in the denominator. So that's going to give me a -6/1. So -3 comma -6. Yeah, that pretty much confirms that I'm going to have a little branch here. So remember, these asymptotes are invisible barriers that can't be touched or crossed. So we're going to keep getting closer to those walls, but we're not going to touch or cross over them. So basically, they are repelling the graph. Now, I do have this one branch that I'm pretty confident about, but I suspect that there could be additional branches in the graph. And I don't know this for sure, but my suspicion is that there may be one diagonal from it up here in this corner. So to kind of test that theory out, I might want to explore what happens when x equals, let's say, -6, and see if I do have any points up in that corner. So when x equals -6, in the numerator I have -6 minus 3. In the denominator I have -6 plus 4. So that's going to be a -9 over a -2, which is +9/2. +9/2 is 4.5. So indeed, I do have a point that I'm going to have to add to the graph. So when x equals -6, then we have y equals 4.5. So let me go up 4, not quite at 5. There's a point right there. So I have the sense that I might have a branch that's going to look like what I have here in the bottom right corner. So to confirm that, let me choose x equals -10. I'm running out of space here. I apologize. I'm just going to keep putting tables of values wherever I can find space. So when x equals -10, I'm going to have to do this one in my head. Y is equal to -10 minus 3 in the numerator. So that's a -13 in the numerator. And in the denominator, I have -10 plus 4, which is a -6. So that's going to give me a +13/6, which is a little bit more than a +2. So when x equals -10, I'm going to be just over +2 for y. And so even with just these 2 points, I think I have enough information to guesstimate that the branch is going to hug these 2 walls like so. So putting together the graph of a rational function is going to start with some of the parts that we've been talking about with vertical asymptotes and horizontal asymptotes, kind of putting up those walls, and then using x and y intercepts to start plotting some points to get a sense for where some of these branches might occur. And then finally, you're going to have to fill in the rest of the shape by finding additional points on the graph to help guide the branches. There's one more question here on this problem, the domain. It looks like x could be any value except for x cannot be -4. Remember that we have a vertical asymptote there, which I'm darkening here for you. So that's the only value of x that's not covered. X cannot be -4. So writing that in integral notation, every real number except for -4 means that we're going to go all the way to the left and all the way to the right of -4, but we're going to skip over it. And so we use open parentheses around -4.